Welcome to the solutions to the Electrostatics Problem Set, problems number 19 through 21. Number 19, if you were asked to design a capacitor for which a small size and large capacitance were required, what factors would be important in your design? And refer to equations on the reference table. If we start with a drawing of a capacitor here, just in a portion of a circuit, parallel plates. I'll explain the green filled in area here in a moment. And the formula for capacitance, C equals epsilon 0 A over D. They want a large capacitance but a small size. What that says to us is that we're not allowed to increase A in order to increase capacitance. So the way, of course, that this would be done according to this equation would be to decrease the plate separation since it has an inverse relationship with capacitance. This would increase the ability of the capacitor to store charge. You could also decrease the voltage between the plates, as it's also equal to Q over V. If you did that, there's an inverse relationship between V and C, so decreasing the voltage between the plates, or the potential difference, would also increase the capacitance. However, there's another aspect here for discussion, and that is there are substances that you can put in between the plates that increase the capacitance of a capacitor. The names of those substances are called dielectrics. This is covered on page 558 of your text. If you take, for example, a substance like Teflon and fill in between the plates with Teflon, that dielectric increases the ability of those plates to store charge, therefore increasing the capacitance. You have a number of substances and a chart there on page 558, which would indicate to you various substances and their ability to increase the charge stored on a capacitor when filling that capacitor in between the plates. On to number 20. Capacitors connected in parallel all have the same charge on them, potential difference across them, or neither of the above. And B, capacitors connected in series will all have the same charge on them, potential difference across them, or 3, neither of the above. Let's start with A, drawing our circuit for capacitors in parallel. And when we draw them, we are reminded the key characteristic of any electrical device in parallel is that each device gets the total voltage delivered by the battery. So the voltage across C1, V1, and the voltage across C2 we'll call V2, and the voltage across C3 we'll call V3, are all equal to each other and equal to the total voltage supplied by the battery. Therefore, the answer to A is that they all have, choice 2, the same potential difference across them. For B, if we draw our series circuit, we are reminded that the key characteristic of any electrical device in series is that the current remains constant in that circuit. And since current is the rate of charge flow, capacitor C1 gets the same charge as capacitor C2, which gets the same charge as capacitor C3. So the answer to B is they have the same charge on them, choice 1, because of that key characteristic of a series circuit. Lastly, number 21. Calculate the speed of a proton that is accelerated from rest through a potential difference of 120 volts. And B, calculate the speed of an electron that is accelerated through that same potential difference. Really neat question because we start to really get into some AP level questions here, applying previous knowledge with electrostatics concepts. This question requires the use of the work energy theorem, where the work done, let's start with A, the work done to accelerate the proton is done by the change in electric potential energy of the proton being the change in kinetic energy of the proton. So another way to express the work done is the change in electric potential energy, and that change in electric potential energy causes a change in kinetic. Well, how do we calculate change in electric potential energy? It would be V times Q, but because it's a change in electric potential energy, it would be delta V times Q. And since the proton started from rest, there is no initial kinetic energy. Therefore, the change in kinetic energy is simply the final value, 1/2 mv squared minus 0, so just 1/2 mv squared. We are told the potential difference was 120 volts. Q is the charge of a proton, 1.6 times 10 to the negative 19 coulombs, equals 1/2 mass of a proton, 1.67 times 10 to the negative 27 kilograms, as found on our reference table, times V squared. Solving for V, remembering to take the square root, we get 1.5 times 10 to the 5th meters per second. B asks us to perform the same calculation, but this time with the electron instead of the proton. So this time, same thing, delta V equals Q, or delta V times Q equals 1/2 mv squared. If it was an electron, the potential difference would be negative 120 volts, because it would be going the opposite direction. Q would be negative 1.6 times 10 to the negative 19 coulombs, since the charge of an electron and electrons are negative, equals 1/2 the mass of an electron off the reference table, 9.11 times 10 to the negative 31 kilograms, times V squared. Solve this for V, and we get 6.5 times 10 to the 6 meters per second. So we see that an electron would be accelerated to a greater speed than the proton would, and this makes sense under the same potential difference because the proton is nearly 1,000 times more massive than an electron, so it should have less speed. A little side lesson here before we end our discussion on these three problems. Sometimes we use an alternate version, an alternate energy unit, to express the energy when we're dealing with a small number of electrons. And that alternate unit of energy is called an electron volt. It's the same concept. We would use the work or change in electric potential energy equals delta V times Q. In this particular problem, the potential difference was 120 volts, but instead of substituting the Coulomb charge of an electron or Coulomb charge of a proton, as in this case, we would just substitute how many elementary charges that is. In the case of A, where the proton, that would be +1 elementary charges. Well, you can see unit-wise what you get is an E times a V, and it would be 120 electron volts, and that is an alternate way to express the energy of this proton when dealing with a small number of elementary charges. And you may ask, well, how small is small? Anything that's 1,000 elementary charges would be, when you consider that a Coulomb is times 10 to the 25th elementary charges, certainly 1,000 elementary charges would be a small number of elementary charges. Just beware of this if you ever see the unit of electron volt used, that it's just being used because we're dealing with a small number of charges. There is a conversion between electron volts and joules on your reference table, where an electron volt is 1.6 times 10 to the negative 19 joules, and that should make sense by analysis of this equation. Okay, more to come on these types of problems when we do numbers 22 and 23 in class tomorrow.